Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today we'll be doing Unit 12, Lesson number 6 on multiplying probabilities. This is the last lesson in our probability unit, but we'll be using probability in the next unit for statistics in order to quantify how likely statistical results were to have happened. So, keep that in mind as we move through this lesson and into the next unit. Let's jump into exercise number 1. All right, so in an earlier lesson, we had a formula for conditional probability. Given the probability of event B occurring, given A has occurred, is this, right? So the probability of B given A is the probability of A and B divided by the probability of B. Answer the following. Letter A says, rewrite this formula, solving for P of A and B. So what would you get if you solved for P of A and B in this formula? Pause the video for a minute and solve for this quantity. All right. Well, it's pretty easy. I mean, to solve for that quantity, we just have to undo what's been done to it, which is division by P of A, and we just get the probability of A and B occurring is going to be the probability of B given A times the probability of A, or vice versa. It doesn't really matter. Okay, in fact, it may make more sense, given the way it's written with A first, to say the probability of A and B occurring would be the probability of A occurring times the probability of B occurring given that A has already occurred. All right, that kind of implies an order. A's got to come first, B's got to come second, which isn't the case. Now, letter B says, how could you write this formula if events A and B were independent? Well, remember, right, the whole idea of independence will be that the probability of B given A is happened is simply the probability of B. So, that then leads me to this formula. The probability of A and B will be the probability of A times the probability of B. All right? This is not only a test for independence, but it's something that we can use if events are independent. If A and B are independent. Now, here's the bigger issue, though. All right? The bigger issue is the word and, not independence or dependence or anything like that. It's all about and. Because what we're going to launch into next are the calculations of more complicated events, multi-stage events, where you have something and something and something and something happening. And what these multiplication rules tell us is how to calculate the probabilities of those larger events. Now, all in all, what we really kind of want to understand is that in probability, there are sort of two scenarios. There's an and scenario, which tells you to multiply, and there's an or scenario that tells you to add. We saw this one earlier on when we were looking at the probability of a union of two events, right? And is more the probability of an intersection. So pause the video now, take a look at this, and then we'll start using these two in the next problem. Okay, I'm going to clear this out. Let's take a look at exercise number 2. Consider the spinner shown below. The spinner is spun twice. Boy, and it's amazing. As soon as we spin something twice, way different, and the result is recorded. Are the outcomes of the two spins dependent or independent? Think about this a little bit. All right. Well, in theory, they are independent. All right. In other words, the outcome of the first spin does not affect the outcome of the second spin. Now, we could get into an argument about physics and, maybe if the first spin lands on an 8, then, it's less likely to end on a 5 the next time. I mean, you could get into endless arguments about that. But in theory, something like a spinner or tossing a coin or things like that, every time you spin, toss a coin or roll a die, whatever, each roll, each spin, each toss is independent of all the others. Now, letter B says, what is the probability that you will get an even on the first spin and a number greater than 5 on the second spin? And boy, is that and important. All right. So I'm going to say even on the first spin, I'm going to capitalize it, and less than 5? Let me go with something different. That doesn't look good. Let's go with less than 5 on the second spin. Well, because these are independent, we can use what we developed in exercise 1. I can just find the probability I'll get an even on the first spin and multiply it by the probability I'll get less than a number 5. All right, getting an even on the first spin, well, that's 4/8 or 1/2, times the probability that I'll get a number less than 5, well, 1, 2, 3, 4. Wait. Less than, oh, sorry, greater than 5. I'm like, wait, something's wrong there. I apologize. It should have been greater than 5. And what would that be? That would be 3 out of 8. All right. And tells us to multiply. So we'll get 12 out of 64, which you could leave it that way, or it can be reduced down to 3/16. Okay, that's it. Now, letter C is more challenging. Okay, this is where probability really starts to get slippery. It says, what is the probability you will spin a prime number and a perfect square in either order? So notice it doesn't say a prime number on the first spin and a perfect square on the second spin. It says a prime number and a perfect square. All right, I'm going to let P be the event of getting a prime number. And I'm going to let S be the event of getting a perfect square. Now, really, the event that we're talking about, getting a prime number and a perfect square, is actually, strangely enough, an OR event, because we'll get either prime on number 1 and a perfect square on number 2, or a perfect square on number 1 and a prime on number 2. All right? And I want to find the probability of all of that. Now, the probability of getting a prime on the first one was what? 2, 3, 5, 7. That's 4 out of 8. 2, 3, 5, 7. And a perfect square, well, what are my perfect squares? Just 1 and 4, right? So 2 out of 8. Now, that doesn't change over here. It's just that the 2/8 comes first and the 4/8 comes second. But now that OR tells me I have to add. Remember, that's a union, right? There's two events that I'm putting together, and those two events are prime 1 and S2, along with, perfect square on 1 and prime on 2. So what do we get? We'll get 8/64 plus 8/64 gives us 16/64, and that gives me a probability of 1/4. There's actually a pretty good chance that I'm going to get a prime number and a perfect square when I spin that twice. Okay? Pause the video and really think about what we did. All right, one more time. I can't emphasize this enough. Anytime you have the word and, in all likelihood, you're going to multiply. And anytime you have the word or, in all likelihood, you're going to add. Okay? So, I'm going to clear out the text. Let's keep working with this. Back side of the sheet. Okay. Exercise 3. A class consists of 12 girls and 8 boys. A group of 3 is picked to give a speech. If the students are picked at random, what is the probability they will be all boys? Use the events below to show how you calculate your final answer. All right? This one's interesting. All right? At the end of the day, what we want, let me not go in green. At the end of the day, what we want is we want this more complicated event. We want a boy picked on the first and a boy picked on the second and a boy picked on the third. So this is the overall event that we're looking for the probability of. So I'm not going to rewrite that. I'll just do something like this. Well, according to our conditional probability, I should take the probability that I got a boy on the first one and multiply it by the probability that I get a boy on the second one, given that I got a boy on the first one, and then multiply it by the probability that I get a boy on the third one, given that I got a boy on the first one and on the second one. All right? Got that? That's really it. Well, what's the probability I get a boy on the first person I pick? Well, there are 8 total boys out of 20 total students. Now, given that I got a boy on the first person that I picked, what's the probability I get a boy on the second one? Well, now there's only 19 students sitting there. And because I picked a boy, there's only 7 boys left. So now the probability is 7/19. Finally, what's the probability I get a boy on the third one, given that I got one on the first and the second? Well, now there's only 18 students to choose from, and only 6 of them are boys. And if I multiply all the numerators together, I get 14. Whoop, I don't get 14. That's just weird. If I multiply all the numerators together, I get 336. And if I multiply all the denominators together, I get 6,840. That's a good probability, although I can't make a lot of sense out of that. Reduced, it's a little bit better. There's my 14. 14 out of 285. That's a good one too. I like them best in decimal form myself. And that's only 0.05, right? Just about 5%. And that's a lot more interesting, right? Because let's say that we had this class of 20 kids. And let's say that picked a group of 3 and they were all boys. The girls might say, hey, wait a second. That seems a little sexist, right? A little discrimination there. Why are you picking all boys? And the teacher might say, hey, look, I just did this at random. I just picked 3 people at random. They all turned out to be boys. Well, how likely is that? Well, that's going to happen only about 5% of the time. Now, it's not impossible. But then again, me playing in the NBA isn't impossible, but it's really, really unlikely. Now, this is a lot more likely than that happening, 5% versus 0.000001%, let's say for me. But there you have it. Okay? So, think about this a little bit. Write down anything you need to, and then we'll move on. Okay. Clear this out. Take a look at number 4. Say a power generating facility has 3 primary safety switches in case of an emergency. Okay, so this is actually an engineering calculation that happens quite often. So you got these 3 safety switches, and there's an emergency, and one of the switches flies, everything's okay. The probability that any one of these switches would fail is 5%. Okay, fine. What is the probability that all 3 will fail, given that the switches are independent of one another? Well, see if you can do that. Okay, pause the video now. Okay, well, I want to phrase this in terms of an and, okay? Because what I really want is the probability that the first one will fail, and the second one will fail, and the third one will fail. I don't want ors there. I don't want to add these things. But the probability that the first one will fail times the probability that the second one will fail times the probability that the third one will fail, right? Because it's all ands. So that's 0.05 times 0.05 times 0.05. That ends up being 0.000125 or 0.0125%. So this is why they build in a lot of safety mechanisms. The individual probability that any one of them would fail is pretty low, only 5%. But to have kind of a catastrophic failure, you'd have to have all three fail. And the probability that happens is right around 1/100th of 1%. Not 1%. Take 1%, divide it by 100, and that's just about the probability that you have here. Okay, very, very low probability. All right, pause the video, take a look, and then we'll finish up with one of the harder problems we've seen. Okay, let's clear this out. Let's tackle one more. All right, using and or. And, you multiply, or you add. All right, it's hard to go wrong with that. Exercise 5. A company was determining the effectiveness of its warranty sales on computers. Hopefully everybody knows what a warranty is, and surely everyone knows what a computer is, because you're watching me on one. They took data on the number of customers who purchased warranties on 2 different brands of computers. If a customer was chosen at random, what is the probability they did not purchase a warranty? All right, so let's make sure that we understand this table before we even attempt to answer this probability question. All right, so we're selling these 2 types of computers, type 1 and type 2. If I closed my eyes and randomly grabbed a person who bought a computer, there would be a 68% chance they bought type 1 and a 32% chance that they bought type 2. Okay, again, make sure you understand that. Because the second column's a bit weird. It says the percent of those who purchased that also purchased a warranty. So, in this case, right, of the people who purchased type 1, 35% of them purchased a warranty. And of those that bought type 2, 56% purchased a warranty. Now, you might notice that these two numbers add up to be 100%. But these two don't, and we wouldn't expect them to. All right, these two we would totally expect to add up to 100% because we're only selling 2 types of computers. 68% of the people who bought a computer got type 1, and 32% got type 2. On the other hand, that 35% and that 56%, that's just the percentage of how many people who bought type 1. You know, you're standing there at Best Buy or some other Circuit City, and hey, you just bought type 1 computer. Only 35% of the people are going to buy that warranty, right, that they offer you at the end. And it's not likely going to be me. So, now it says, if a customer was chosen at random, what is the probability that they did not purchase a warranty? Okay. Oh boy. Well, pause the video and see what you can do with this problem. Then we'll walk through it. All right, let's play around with it. Well, if a customer did not purchase a warranty, they sort of fell into 2 categories. They got type 1 and no warranty, or they bought computer type 2 and they got no warranty, right? So that's what I'm trying to find the probability of, right? Here's my event. Now, these two events don't overlap at all because type 1, type 2, you either bought one or you bought the other. So ultimately now I have to calculate the probability of type 1 and no warranty plus the probability of type 2 and no warranty. All right, so that OR is going to force me to add two probabilities. Then the question is, well, how do I calculate this? Well, I'm going to find the probability that they bought type 1 and multiply it by the probability that they got no warranty given that they bought type 1. Then I'm going to find the probability that they got type 2 and multiply it by the probability that they got no warranty given that they bought type 2. See, these no warranty and the types, those are not independent of each other. Well, I'm running out of room, but the probability they got type 1 was 0.68. Now, what was the probability that they got no warranty given that they bought type 1? Well, that's 0.65, right? This is the probability that they got the warranty. The probability they didn't get the warranty would be 100 minus 35, or 65%. 65% didn't get the warranty. Now, the probability that they bought type 2 was 32%, and the probability that they didn't get a warranty based on the fact that they got type 2 was 0.44. Yep, just making sure that's all good. All right, that first product comes out to be 0.442. The second one turns out to be 0.1408. And when I add them together, we get 0.5828. And that's the probability that a person picked at random wouldn't have bought a warranty. All right, and that's it. That's tricky, putting together ands and ors and all sorts of different things. Pause the video now and think about what we just did. All right, let's clear that text out and let's wrap it up. Okay, so today we saw how to use the multiplication of probabilities to calculate the probability of multi-stage events that involve and. Right? And this can be used all over the place. I mean, if I was going to flip a coin 3 times and I wanted to know the probability it landed on a head each time, well, 1/2 times 1/2 times 1/2, right? Head on the first throw and head on the second throw and head on the third throw. So you'd multiply those probabilities all together, right? And you can do this all over the place. You know, I roll a die and I want to know the probability I got an even and then I got a 6. You know, you could, well, 1/2 that I got an even and 1/6 that I got a 6. So 1/12 that I got an even and then I got a 6. Right? So multiplying probabilities is critical when you have events that involve and. On the other hand, we also reviewed the idea that if you have events that involve or, you add probabilities. All right. Well, thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.